Okay, let's look at a couple of examples of how to use the limit definition of the derivative. Here's one. In this example, we need to use the limit definition to find the equation of a tangent line to the graph of a given function at a given point. Now, let's think about this. If we're after the equation of a line, tangent or not, what types of information would be sufficient to find that equation? Well, we could find the equation of a line given 2 points, or given a slope and a point. And looking at the information we have, we know 1 point, namely 2, 0, that it has to pass through. How about the slope? How will we get our hands on its value? Well, of course, that's exactly what the derivative is designed to do. It's designed to give us slopes of tangent lines at a particular x value. And we have, of course, the x value in question, namely 2. So the slope we're after should be equal to the value of the derivative at 2. Presuming, of course, that my function is this guy right here. F of x is x squared minus 3x plus 2. So we just need to find the derivative and then plug in 2. Now notice in the question here we're asked to use the limit definition of the derivative. No other tricks to find it. So maybe we need to recall what the limit definition of the derivative says. Notice we define f prime of x to be the value of this limit here, provided it exists. So let's see if we can't flesh out this limit in the context of this particular function. So f prime of x is going to be the limit as h goes to 0. Remember, h is thought of as a little tiny change in x of the difference between f of x plus h and f of x over h. Basically, this is a rise over a run. Let me put this off to the side, as I think we'll need the room. And let's reinterpret this in terms of this function. So we have the limit as h goes to 0 of f of x plus h. Now what is f of x plus h? Well, how do we find f of anything? We take that thing, that input, and plug it in for every occurrence of our input variable here where our function has been defined. So we need to take that input and square it. We need to take that input and multiply it by 3 and subtract that quantity. And we need to add 2. And then, of course, we should clean that up a little bit. So, for example, this can be expanded. That's x squared plus 2xh plus h squared minus 3x minus 3h and plus 2. So all of that is what I need in this position right here. And that's a lot to write, so let's go ahead and crank it out here. But remember, that's just this first piece. There's another piece over here. We need to subtract off f of x. And we know what f of x is. It's sitting right there. Okay. Be careful when you do this subtraction that you put this function in parentheses. It's very, very easy to lose a distributed negative there. And the parentheses will help you not lose that. And then, of course, all of this is sitting over h. So this is the limit we have to crank out. But keep in mind, we can never immediately turn this limit of a quotient into a quotient of limits, because the bottom, the denominator, as h goes to 0, this denominator goes to 0. So we have to find another way. Hopefully this h will cancel off with something. Presumably a factor of h in the numerator. But of course that presupposes that our numerator is in simplified and factored form. So maybe that's what we should do next. Let's go ahead and simplify this top. Notice we have an x squared minus an x squared. So these two terms cancel off. We also have a negative 3x minus a negative 3x, or plus 3x. So again, those two will cancel off. We also have a plus 2 minus 2 over here, so those two cancel off. So, rewriting what's left, we have 2xh plus h squared minus 3h, and all of that is over h. And again, we're hoping this h cancels off with a factor of h in the numerator, and sure enough, notice all of these terms have an h on them, so we can factor that out. So we have the limit as h goes to 0 of h times 2x plus a single h minus 3, all of that over h, and now we can cancel our h's. And what we are left with, notice, is a polynomial in terms of h. And so to evaluate the limit as h goes to 0, all I have to do is plug in h equals 0 into this expression right here. And that, of course, gives me 2x plus 0 minus 3, or just 2x minus 3. Okay, so that is our f prime of x. However, I don't need f prime of x, I just need f prime of 2. So I can take this value of 2 and plug it into here to find that the slope I need is simply 1. So, how do I find the equation of a line that goes through point 20 and has slope equal to 1? Well, the easiest way to get there is through the point slope form for an equation of a line. And if you recall, that is y minus y naught equals m times the quantity x minus x naught, where x naught y naught is the point in question, and m, of course, is the slope. So plugging in the information we have, we'd have y minus 0 equals m, which is a 1, times x minus 2. And then cleaning that up even further, we have y equals simply x minus 2. And that right there is the equation of the line we saw. Okay, let's look at another example. In this one, we need to use the limit definition to find the equation of the normal line to the graph of this new given function at this particular x value. Recall, the normal line is simply the line that is perpendicular to the tangent line, in this case at x equals 3. But whether you're after the equation of the normal line or the tangent line doesn't really matter a whole lot as far as the strategy goes. If you're after the equation of any line, you need two pieces of information. You need a slope of that line, and you need a point that it passes through. Now, last time we were given the point explicitly. What about this time? All we're told is x is 3. So I suppose we have the x-coordinate of the point in question. But how do we find the y? Well, we find it the same way we always find y-coordinates, or the height of the graph of the function at a particular x value. We simply plug that x value in. So here, that should be 1 over the square root of 4 minus 3, or 4 minus 3, of course, is 1. The square root of 1 is 1, so this is simply the point 3, 1. So we have to pass through this point. Now, what about the slope? Remember, the slope of the normal line must be perpendicular to the slope of the tangent line. And the slope of the tangent line is something we can get our hands on through the derivative. In fact, the slope of the tangent line should be the value of the derivative at 3. That is to say, the slope of the tangent line should be f prime of 3. But the normal line should have a slope that is perpendicular to this. And if you recall from algebra, perpendicular slopes are negative reciprocals of one another. So I have to take this value and flip it, i.e. reciprocate it, and negate it. So that's the slope I'm after. Of course, to actually get the value here, I will need to figure out what f prime is doing. And that's where our limit definition of the derivative comes in. Recall, we can find f prime of x if we simply evaluate this limit. The limit as h goes to 0 of f of x plus h minus f of x, all of that over h. Very important that you can rattle that off very quickly. Now, what does this mean in the context of this function? Well, let's write it out. So we have the limit as h goes to 0 of f of x plus h. Let's see, what is f of x plus h? Let me write that up here. It's kind of out of the way. Remember, all we have to do is take the input and plug it in for every occurrence of our input variable where our function is defined. So this should be 1 over the square root of 4 minus the input, 4 minus the quantity x plus h. And be careful you put that in parentheses there so you don't lose that distributed negative. So taking that piece and putting it down here, we have 1 over the square root of 4 minus, and let me go ahead and distribute it now, minus x minus h minus f of x, which is right here. That's 1 over the square root of 4 minus x. And then, of course, all of that is sitting over h. Now, again, we can't simply plug h equals 0 into this. We can't rewrite this as a quotient of limits because our denominator is going to 0. So I have to find some other way. Ideally, this factor of h in the denominator will cancel off with a factor of h in the numerator, but it looks like I have some work to do before I can find that canceling factor, because the top right now is a mess. I'm going to have to clean up the top before I can see that factor. I need to get it into a simplified and factored form. Now, one step we can do to get closer to that is to combine these two fractions in the numerator into a single fraction. Of course, that requires getting what? Down here. We need common denominators, don't we? So with that in mind, let me spread these guys out a little bit. There we go. And then let's ask the question, what is this denominator missing in terms of a factor that this denominator has? Well, of course, it's missing this. So let's go ahead and throw that in the denominator. Of course, I can't just put it in the denominator without altering the expression, so I also put it in the numerator, so we're really just multiplying by a well-chosen value of 1, which doesn't affect anything. And then let's ask the same question over here. What is this denominator missing in terms of a factor that this denominator has? And of course, it's all of this. So let's throw that in to the denominator here. And again, play fair here, put it in the numerator. So we're really just multiplying by a well-chosen value of 1 and not altering the expression in any way. Now, notice these two fractions, when we multiply them together, have a common denominator. So we can jam these two things into a single fraction. So now we have the limit as h goes to 0 of the square root of 4 minus x right here, minus the square root of this mess, all of that over this common denominator, and all of that sitting over h. Of course, recall, if you have a fraction a over b divided by some c, we can rewrite that as a over b times the reciprocal of c, or a over bc, so I can simply take this denominator here and move it up to here. So let's go ahead and do that. Okay. So that's a little better. At least we don't have fractions inside of fractions like we did before. But this top is still not in a factored form, one that would allow me to possibly cancel an h. So to get it in that form, we take advantage of a trick here that's tied to radicals, in particular sums and differences involving radicals. And that is, we're going to multiply by the conjugate here of the numerator. That is to say, if this is a minus b, we're going to multiply by a plus b. So in this particular case, I'm going to multiply this numerator by the square root of 4 minus x plus the square root of 4 minus x minus h. Again, though, I can't just multiply the numerator by that and leave the expression unchanged, so I need to multiply the denominator by that mess as well. And again, these parentheses are very handy here. Make sure you include them. Now, the numerator, when we multiply it out, is a difference of squares. And now you can see why this trick is helpful. A minus b times a plus b is simply a squared minus b squared. The net effect is I'm going to square both of those radicals away. So we have the limit, as h goes to 0, of 4 minus x, right? This guy squared minus this guy squared. Again, watch those parentheses. Go ahead and put them in. The squaring is going to get rid of the radical, but you'll need to worry about this negative distributing through this expression. So that's why the parentheses are important. Okay, so that's the product of those two things. On the bottom, we have a bunch of stuff now. But I'm going to leave this in its current factored form. And again, this is on purpose, even though it's a mess. Because, again, we're interested in seeing this h go away. It's only going to go away if we cancel it off. And it can only cancel it off if we see a common factor of h in the numerator and h in the denominator. But if I multiplied all this out, I'm going to lose the ability to see this as a single factor. So we leave it in factored form. Now, look at the numerator. Some nice stuff happens here, right? Notice we have a 4 minus a 4. Those cancel. We have a negative x minus a negative x. Those cancel. We have a minus a negative h. The negatives kill each other off, and so we're left with simply an h. That's our single factor of h we hoped we would see. That will cancel off with this h down below. So let's cancel the h there and there. And let's scroll down just a wee bit so we have some room to work here. And notice all we have left, let's move this out of the way too. All we have left here is, let's see, what do we have left on the top? The h is canceled. That should just leave a 1, right? Then we have this other stuff here. But as messy as this still looks, we're actually in really good shape. Recall, our initial problem was we couldn't express this limit of a quotient as a quotient of limits because the denominator was not going to something non-zero, as h went to 0. Now we don't have that problem. And in fact, what we have down here in the limit as h goes to 0 should be identical to this expression with h equals 0 plugged in. Okay, and of course we can quote plug in h equals 0 up top too. Of course that just leaves a 1. This is the limit of a constant function up top. Okay, so what do we have down here when we plug in h equals 0? This is the square root of 4 minus x minus nothing, so just the square root of 4 minus x. But then there's another square root of 4 minus x here. So multiplying those two together, we should get 4 minus x back. And I'll put that in parentheses because we still have another factor over here. This is the square root of 4 minus x plus, and then again, if h is 0, that's the square root of 4 minus x. So we have one of these guys plus another one of these guys. That's two of those guys. Now, you might want to write this in a little bit nicer form here because we notice we have a 4 minus x. That's to the first power. This is another 4 minus x to the half power. We could combine those two things to say we have a 4 minus x to the 3/2 power in the denominator. So we have 1 over 2 times 4 minus x to the 3/2. There is our derivative. However, that's not our final answer. Remember, We just wanted the formula for the derivative, the formula for f prime of x, so we could figure out what f prime of 3 is. So the slope here should be negative 1 over f prime of 3, which means I need to plug in 3 here. Of course, 4 minus 3 is 1, 1 to the 3 has power is 1, so we're looking at 1/2. So the slope we require is negative 2. However, notice that's not our final answer either. We needed the slope and a point that we could put together to find this equation of the normal line. And here again, the best way to get to the equation of the line is to use the point slope form, which is y minus y naught equals m times x minus x naught, where x naught, y naught is that point right there, and there's our slope. So it looks like we should have y minus 1 equals our slope of negative 2 times x minus 3. Okay, if you want to solve that for y, that's fine. Let's see, we would have, distributing this, negative 2x plus 6, but then we're going to have to add the 1 as well. Let's go ahead and write this in 2 steps, I guess. So y equals negative 2x, and then adding the 1 plus 7. And that right there is the equation of the normal line. Okay, let's consider one more example. Here we're asked to use the limit definition of the derivative again, only this time to find all points on the graph of this given function here, where the lines that pass through these points and are tangent to the graph have slope 0. In other words, they are horizontal tangents. To clarify what we're after, suppose we graph this function, say on a calculator or a computer. We should see a graph that looks similar to this red curve here. What we're after are the points like this one and this one, where if we were to draw a tangent line to the graph through that point, like this dotted one for this point, or in this case it looks like it might be the axis itself, where those lines are horizontal. They have slope 0. Notice those are the only 2 points where that occurs. If we pick any red point over here and draw the tangent line, it looks like it should be steeply sloped upward. If we pick any point in this region, notice the tangent lines would be sloped downward. They'd have a negative slope. Over here again, anywhere along this interval, it looks like our tangent lines would again be sloped upward or have a positive slope. Now, asking questions like this turns out to be very important, and we'll see this again later on, as not only does it tell us a point where we have a horizontal tangent, but it also tells us the point at which our function achieves its maximum value in some interval, or, in the case of this point, a minimum value in some interval. Just as a precursor of what's to come, we call such things local maximums and local minimums. But back to the problem at hand. We need to find out where are these points where we have horizontal tangents, where the tangent has slope 0. Well, again, how do we get our hands on the slopes of tangent lines to this curve? That's what the derivative gives us, right? So we are searching for x values that when I plug them into the derivative, I get out the slope of the tangent line, I get out a slope of 0. So I'm trying to solve this. Of course, that requires some knowledge of what f prime of x is. So we're going to have to crank that out, and we can use the limit definition of the derivative to find it. So let's move this out of the way. I think we'll probably need the space here. Recall how the derivative is defined. It's the limit, as h goes to 0, of f of x plus h minus f of x, all of that over h. Again, you need to be very quick to recall this. Now, in the context of this particular function, what does this mean? Well, again, we have the limit as h goes to 0 of some big fraction here. The first piece of our numerator is f of x plus h. How do we find that? Well, we take our input, which is x plus h, and we plug it in for every occurrence of our input variable to discover that this should be 4 times x plus h cubed, right? Our input cubed, minus 12 times our input squared. Our input again is x plus h, plus 9 times our input, and then minus f of x. We know what f of x is. We have to subtract all that. And again, it's a good idea to use parentheses when you make that substitution, lest you forget about distributing this negative through. And then, of course, all that's sitting over h. Now again, we can't simply treat this limit of a quotient as a quotient of limits because the denominator is going to 0 in the limit. And so I have to find another way. Hopefully I can get this h to cancel off. Hopefully I will see it as a common factor from the numerator and the denominator, but that requires the numerator be in factored form. And if I'm going to get the numerator in factored form, I better simplify it, because right now we've got a mess. Okay, so let's expand this out. We still, of course, have the limit as h goes to 0. This piece here is 4 times x plus h cubed. If you recall your special product rules, that should be x cubed plus 3x squared h plus 3xh squared plus h cubed. Of course, you can FOIL it out if you need to. Minus 12 times a perfect square here, so that's x squared plus 2xh plus h squared, plus distributing the 9 there, plus 9x plus 9h, and then distributing this negative, we have negative 4x cubed plus 12x squared and minus 9x, all of that over h. Again, we're trying to get this numerator in factored form, or at least see a factor of h in the numerator so we can cancel it off. We still need to simplify further. We can do this distribution of 4 and 12 here and see what happens. So we have limit as h goes to 0 of 4x cubed plus 12x squared h plus 12x h squared plus 4h cubed minus 12x squared minus 24 xh minus 12h squared, and then all of this. And again, all of that is sitting over h. Okay, looks like it's just getting worse and worse, right? However, notice what happens. We have a 4x cubed minus a 4x cubed. Those drop off. We have a negative 12x squared, and we have a positive 12x squared. Those cancel off. And we have a 9x and a minus 9x. Those cancel off. So a lot just dropped off here. And further, notice there is an h on every single one of the terms that are left, which means I can factor that h out and hopefully cancel it with what's below. So doing that, we have the limit as h goes to 0 of h times 12x squared plus 12xh, don't forget there's 1 left over there, plus 4h squared, 2 left over there when we pull one of them out, minus 24x minus 12h, and finally plus 9, all of that over h. And our wish has come true. Our factor of h cancels in the numerator and the denominator. And so now all we're looking at is the limit of what is a polynomial in h. And we know we can find limits of polynomials simply by plugging in the value here, in this case 0, in for h. So let's see what happens when we do that. Of course, this remains 12x squared. Here, 12x times 0 is 0. That goes away. 4h squared, that's 4 times 0 squared. That also goes away. Minus 24x, minus 12 times 0, that goes away. And finally, plus 9. And so that is the derivative. Keep in mind, that's not what we were after. This is just a means to an end. Remember, I wanted the derivative so that I could solve for where the derivative is 0, because that's when I have a tangent line of slope 0. So what we need to do is solve for where this equals 0. Okay, so let's scroll down here a little bit so we have some room to work. Okay, so we set this derivative equal to 0. We want to solve for which x values satisfy that, and we do that in the normal way. This is a nice quadratic here. 0 is on the other side, so maybe we attempt to solve this by factoring. Notice we can pull a common 3 out. That leaves 4x squared minus 8x plus 3. And then this in turn hopefully will factor, and I believe it does, into two binomials. Let's see, to make 4x squared we might use a 2x and a 2x. To get a 3 we'll probably need a 3 and a 1. And to make these signs work out and this middle term work out, as we have 6x there as our inner product and 2x as our outer product, let's make them both negative. And that will give us a negative 8x there. And so then this tells us that either the factor 2x minus 3 equals 0, or 2x minus 1 is 0. So x must either be 3/2, solving that one, or 1/2, solving that one. And let's write this a little bit better. Let's say, or x equals 1/2. So, going back to our picture here, we just found x equals 1/2. That's where this guy happens. X equals 3/2. That's where that guy happens. Okay? However, these are x values, and we were asked to find all points on the graph. I need not only the x value, but I also need the y value for those points. How do I find the y value for these particular x values? Well, the same way we always find y values. We go back to our original function, plug those x values in. So again, scroll down a bit so we, oops. Okay, so giving ourselves a little more room here. When x is 1/2, notice f of x is going to be 4 times a half cubed minus 12 times a half squared plus 9 times a half. And that in turn equals a half minus 3 plus 9/2. Combining those, that's 10/2. That's 5. Minus 3 is 2. And when x is 3/2, looks like f of x is going to be 4 times 3/2 cubed minus 12 times 3/2 squared plus 9 times 3/2, which if we simplify all that, we get 27/2 plus another 27/2, that's 27, minus 27 is 0. So we have an x, y pair there, and an x, y pair there, and so the 2 points that we seek are 1/2, 2, and 3/2, 0. And they are the only points with horizontal tangents. That is our answer, and we are done.